Welcome viewers, welcome to the new lesson from Dr. Arts Biology. If you did not subscribe the channel, you can just click on the subscribe button and bell icon. Welcome students. So far we have learned about the different types of glycosidic bond and different types of disaccharides. Now we are just moving into polysaccharides, and we have learned in the first lesson of the carbohydrate that polysaccharides are nothing but the carbohydrate which are composed of 10 or more monosaccharide unit. We can just classify polysaccharides into two types, homopolysaccharides and heteropolysaccharides. As the name indicates, homo means the same. So, the homopolysaccharides are the polysaccharides which are composed of monosaccharides which are the same. So, if the polysaccharide is composed of large number of similar monosaccharides, it will be known as the homopolysaccharide. If it is composed of more than one type of monosaccharide, it will be known as the heteropolysaccharide. Hetero means different. Okay, so let us see the homopolysaccharides here. So we have to learn, as per the syllabus, we have to learn two examples that are nothing but the glycogen and the chitin. In addition to that, I am just mentioning starch also, so that you will understand what is the exact difference between glycogen and starch. Okay, so these two only you have to learn. This is just for your knowledge only. It is not for your syllabus or not for your examination. Okay, so let us see the glycogen first. We know that the glycogen is actually the stored polysaccharide or storage polysaccharide. The storage polysaccharide in animals. And we can see that in our case, we can just see the storage polysaccharides in liver as liver glycogen. And in case of the muscle glycogen. So which are actually the reserve food material for the emergency situations. Whenever the glucose in your blood is going down, your liver will be releasing glucose by hydrolysis of glycogen. Your muscle will be releasing glucose by hydrolysis of glycogen. And that process is known as the glycogenolysis. Glycogenolysis, where breakdown of glycogen will be happening, and as a result the glucose will be released into the blood. We know that the glucose is the only energy source for the brain, and if glucose is not there in the blood, the brain cells will be dying. So in order to avoid that, glycogenolysis will be happening. And as a result, the glucose will be releasing from the glycogen that is stored in liver and muscle. Now, the opposite way. Suppose if you are having a meal, your blood glucose level will be increasing. That increased amount of blood glucose should be taken out from the blood. Otherwise, it will be creating problem called diabetes mellitus. So, in order to avoid that, the glucose will be uptaking from the blood, and as a result, it will be storing in liver and muscle in the form of glycogen. And that process is known as the glycogenesis. And we know two hormones which are involved in these two particular processes. What are they? Glycogenolysis is actually the glucagon. And the glycogenesis actually with the help of insulin. Okay, so that's how the glycogen is acting as the storage polysaccharide. That is the function of glycogen itself. So we have learned the function of glycogen. Now let us see the structure of glycogen. In order to see the structure, we have to remember what are the bonds which are involved in and what are the components. We can see that the component is a homopolysaccharide. So only one monosaccharide is there, and that one monosaccharide we have already mentioned here. Glucose is released, glucose is added to form So what will be the component? It is nothing but the glucose. Now the question is, what are the two types or what are the types of glycosidic bond where glucose is linked to form the glycogen? There are two types of glycosidic bond that you can find in case of the glycogen. One is for linear polymerization and the second one is for branching. Okay, so the bond will be of two types then. First one is the alpha 1,4 glycosidic bond, and that is for linear polymerization. And the second thing is alpha 1,6 glycosidic bond, and that is for branching. So for the branching, the glycosidic bond is alpha 1,4, and for the linear polymerization, the glycosidic bond is, so branching alpha 1,6 and the linear polymerization it is alpha 1,4. Now let us see the structure of glycogen. I will be just drawing the structure to represent both this bond only, not the entire glycogen, because we know that it's a polysaccharide. Large number of glucose is there. So I will be just representing structure with a dotted line for entire molecule, and only I will be drawing the glucose unit where you can find alpha 1,4 linkage and alpha 1,6 linkage. Okay, so branching, I have mentioned the branching. Now the question is how frequently you can find the branching. So each 8 to 10 unit of sugar, so we'll be having a branch. So branching frequency will be like the branching will happen at each 8 to 10 glucose unit. So let us see the structure. So you can see glucose here. I'm just drawing here so that I can draw the branching. So one glucose unit, we know that it is alpha 1,4 linkage, so alpha configuration only. So two glucose units are linked to alpha 1,4 linkage. I'm just putting it dot for the next polymers, and here also we can find HO. I'm putting dot, and then H, OH, OH, H, OH, H, H, OH, and there is H, and what should be the, okay, so CH, I'm just writing CH2OH here, and I'm just marking the, so this one is alpha 1,4 linkage glycosidic bond. I'm here marking the branching H. We know that CH2OH, we did not draw the branching before, right? So I'm just using the different color. CH2 is there, and we know it will be linked with the OH. CH2OH is actually the OH. Now I need another glucose residues that is passing here through. Okay, so alpha 1,6 linkage is there. So another glucose molecules branching is happening. So O, okay, H. So it's another linear polymer that is going to link with this particular linear polymer. So we are having again one OH. Sorry, this one is actually, we know that the anomeric carbon will be attacking the hydroxyl oxygen. So we have to represent the red one here, OH. Red one OH here. And we will be just representing H, O, that is linked to this CH2. So CH2OH, and here is the HOH. Remaining will be same. H. So you can find one polymer, linear polymer here, and the second linear polymer here. The first linear polymer is linking with the second linear polymer to form the branch, and you can find the branch formation here. So what will be happening? This particular thing, this particular H and OH will be released in the form of water. So this one will be released in the form of H2O. Now what is left there? The carbon, oxygen. So the bond will be formed between this carbon and oxygen. So I'm just erasing and drawing. So if you did not get it, you just rewind the video and then watch it. So there will be a formation of link between the oxygen of H2OH and the first carbon. So as a result, the bond will be looking like this. So there is a bond. Okay, so this is actually the alpha 1,6 linkage, which is formed as a result of release of water. Okay, so that is what actually mean by the alpha 1,6 linkage. So you have to draw the glycogen structure if it is asked for the exam in this way, and only 3 sugar unit should be, glucose unit should be there, and the remaining you can just represent with the dotted lines. Okay, there is no sugar after this. Once the branching point is there, it will be moving like this. Okay, so that's about it. So that's about the glycogen. Hope you understood what is glycogen, what is the structure, what are the bond involved, and what is the function of glycogen. Now let us move to the chitin. So chitin, we already discussed about the chitin as part of the N-glycosidic bond. You can find the N-glycosidic bond in case of the chitin in order to form the N-acetyl glucosamine. So we can see here. So chitin is actually homopolymer only, homopolymer which is composed of N-acetyl glucosamine. So where we can find chitin? Chitin is actually the structural polymer, structural polysaccharide. We have learned the glycogen as the storage polysaccharide or the storage molecule or the metabolic molecule. Here chitin is actually the structural polysaccharide where it forms the structural component of organism. Where we can find chitin? We can find in case of larva, that is in case of the fungus. We can see the chitin in cell wall of the fungus. In case of arthropods, we can see in exoskeleton. Exoskeleton of lower organism we can find, for example, arthropoda. You can find chitin. You can find chitinous teeth and all those things in other organisms also. So chitin is a structural polysaccharide, and that will form the hard part. It forms the cell wall in case of the fungus, it forms the exoskeleton in case of the invertebrate organisms. Okay, now the question, as we discussed before, what are the components of chitin? So chitins are composed of N-acetyl glucosamine. So we have discussed it in case of the N-glycosidic bond. So N-acetyl glucosamine is the component of chitin, is homopolysaccharide. Okay, so now the question is how the N-acetyl glucosamine is linked to form the chitin. So it is actually with the help of glycosidic bond, that is nothing but beta 1,4 glycosidic bond. So beta 1,4 glycosidic bond is linking the N-acetyl glucosamine to form the chitin. Hope you got it. Now let us see the structure. So here we can see first of all the chitin. So the N-acetyl glucosamine should be there. N-acetyl glucosamine is nothing but this particular structure, NC double bond OCH3, and the glucose is in beta configuration. Don't forget that. So H and then OH, H, OH. then CH2OH H. So it will be having OH here. Now a second polysaccharide. As I am representing the chitin, it's a polymer. I am just linking this particular thing with the O in this way, dotted line, so that we are representing so many units of N-acetyl glucosamine is there that form the chitin. Okay, it's linking with the another N-acetyl glucosamine. Okay, that 2 in beta configuration, H NH C double bond O CH3 H OH H H O H H O H. Now the remaining portion CH2OH H. So it is one N-acetyl glucosamine. This is already a polymer of N-acetyl glucosamine. So I am just linking this to N-acetyl glucosamine. We can see that just like we have learned about the beta glycosidic bond, we can see that this molecule will be released in the form of water. So this water will be released out. As a result, the bond will be formed. I am just erasing and drawing. So as you are with book, you have to redraw it. You just draw this first, and in the next drawing you have to mention the bond. Then only it will be clear for you. So I am just drawing the beta 1,4 glycosidic bond. So this will be O. Okay, so they formed the beta 1,4 glycosidic bond. So this one is beta 1,4 glycosidic bond that is formed as a result of release of water. So you have to keep in mind that all the glycosidic bond can be we can break all the glycosidic bond with the help of addition of water. That is known as the hydrolysis. We can see that most of the enzymes are hydrolytic in nature. They will break the molecule by adding water, because all the bond in biomolecules are mainly formed with the release of water. Okay, so this is the chitin. Now the question is how starch and glycogen is different. We can see that in case of the starch also, glucose is the component monosaccharide and they are linked through alpha-1,4 linkage. They have branched through alpha-1,6 linkage. Now, where is the difference between glycogen and the starch? You can draw the structure of glycogen and starch in the same way. But where is the difference? Difference is only in the frequency of branching. Frequency of branching in case of the starch is comparatively lesser, and it will be at each 30 glucose unit. You can find branches in starch, amylopectin, at 30 glucose unit. In case of the glycogen, it was 8 to 10 glucose unit. That is the only difference between starch and the glycogen. And one more content is starch is having two types: amylose, which is unbranched polymer. We cannot find alpha-1,6 linkage in amylose, and amylopectin is the which is branched. That you can find alpha-1,6 as well as alpha-1,4 linkage, where the branching occurs at each 30 glucose unit. So that's about the homopolysaccharide. Hope you got the idea. So when you are learning polysaccharide, you have to learn what is it, what are the two types of polysaccharide. First one is homo and second one is hetero. What is meant by homopolysaccharide and what are the examples. In example glycogen, you have to learn the function plus structure, and then chitin, function plus structure. So what are the bond involved, what are the components, etc. So that's about the homopolysaccharide. Now let us move to the heteropolysaccharides.